So our weight, we're setting at 10,000 kilograms. It's the same as the PBY Catalina. We really can't pretend to be lighter than that when there's a precedence for a boat that's a flying boat that size with that mass. And the fuselage diameter that we chose, the kind of sized us with the Catalina, that's due to the thermal requirements of our energy source, which we're planning to use 2 or 3 of the MMRTG, just sort of standard thermal generators. Our length is about 18 meters, and that's what the Starship can accommodate. And when we unfurl those wings, we're looking at a 25-meter wingspan or 75 square meters of area. For level flight, it looks like we're going to need 10 kilowatts for this size and weight, and we could climb 500 feet a minute up to the clouds with 40 kilowatts. Now, when you do the math on this, that's about 2 Earth days to charge for 1 hour of flight time, a level flight. And then if you wanted to fly to the higher elevations, which the clouds are about 30 kilometers up on Titan, the ones that make rain, I should say. If you wanted to get to those, you'd have to charge for the better part of an Earth month. And then the next thing was, what if each of these sections in the inflatable wing were actually a soft robotic actuator? And this could let us basically carry more load before buckling because you have sort of an active control over the stiffness of that member. And also you could warp the wings like the Wright brothers did and have just that built-in control surface actuation. So as a boat, this is our flying boat here. The water line is about 1 meter. It's sits a little bit deeper in the water than you would expect on Earth. The liquid methane on Titan isn't quite as dense, and so you do displace a little bit more. But I think it's actually a pretty reasonable setup there. The one thing we found when we did the math on this, actually, it's kind of interesting. The planing speed, where you get up to plane with a boat, where you're on plane, right? That's twice our cruising speed in airplane mode. And so when we get up to speed to fly, it'll just pick us up out of that liquid. We won't be planing at all. Now here's an example of 2 cones, sort of just to show how we can do some of this fluid transport. Now, in reality, with the cactus rod, you're going to have a tangential area between one tapered surface and another, and we're approximating that here with these concentric cones. There's another cool thing we learned. This was an early thing in the project, the capillary rise between a flexible wall and a rigid wall. And this paper shows the setup where they have like a glass plate, and then in the front they have a flexible membrane hanging, and it's spaced out with little spacers, and then they introduce it to a capillary fluid and it climbs up in the gap. And what it does is the fluid can actually deform the membrane to the shape that helps it rise. The capillary force will pull it closer. And so on the right, on a time scale much larger than 500 seconds, this thing goes to 5-6 inches, and it just keeps going. Much more than the Jurin height. So here's an example. So we were able to do this in Surface Evolver. On the left, we have more of a thicker gap or radius. And on the right, we have a tighter radius, like to represent when the liquid would pull that membrane closer together with its own capillary force. We can only do fixed thicknesses at once right now. Oh, this is a cool one. We showed with a numerical simulation that if you have a perfect torus on a cone, a water drop, it's a perfect torus, it's inherently unstable. Now, this did show up in the literature. We were able to simulate this in Surface Evolver. After it gets going here, it immediately chooses to be in a toroidal shape, as we see here. And this is an unstable equilibrium. The literature does show this. It is an equilibrium position. They did notice that it's not perfectly stable, but what we've shown here is that every single time it moves away, and now it's moving to the right. And so really it looks like an equilibrium solution, but it's so unstable it practically can't stay there at all. What's next for TitanAir? Well, we're going to move away from leading edge collection and focus on lower pressure aerodynamic surfaces. And the reason why is, like with the kite experiment, we found that the condensation was on the trailing edge because I installed it backwards. So what happens, the leading edge has the stagnation point, and you get higher pressure there, and you get adiabatic heating, which makes you less likely to experience condensation. In a lower pressure area, you're going to have adiabatic expansion and cooling, which makes you more likely to have condensation there. We're going to do a deep dive into the thermal balance situation to optimize the fuselage diameter and see if we can get that mass away from the Catalina down to something a little bit lighter. And we want to work with student design teams to develop a trifibian vehicle. So anyone in the audience, if you are at an educational institution or if you're a student, feel free to email me. We're working on that actively this year. And we also want to look at science payload opportunities for aerosol measurement, and we're going to really look heavily at Earth atmospheric science and how we can do that. And we also have to look at competing approaches. We can't forget that. So maybe dragonfly with pontoons. Maybe I've seen a flying dinghy where someone put a wing on an actual rigid inflatable hull boat, very lightweight boat.